this video, we'll be working with Taylor series. And Taylor series, as we've seen in the last video, are very special series representations for certain functions. Probably the most common functions we work with are e to the x, sine x, cosine x, ln of x plus 1, 1 over 1 minus x, and 1 plus x to the r. So we'll just kind of briefly take a look at summarizing the power series that we've seen, whether it's in a previous video or some homework. These are like our key identities. And there will be a chart of these included in your course as well to go ahead and print out and just familiarize yourself with those. The e to the x is x to the n over n factorial. Sine of x is negative 1 to the n, x to the 2n plus 1 over 2n plus 1 factorial. Cosine of x is negative 1 to the n, x to the 2n over 2n factorial. Ln of x plus 1 is negative 1 to the n minus 1 over n, x to the n. 1 over 1 minus x is x to the n for on the interval negative 1 to 1. 1 plus x to the r is called our binomial series, and it's described by this combinatorial factor, r choose n, x to the n, for absolute value of x less than 1. And a way to expand that is with this formula. 1 plus r times x plus r times r minus 1 over 2 factorial x squared, so on and so forth. The general terms formula is given by r times r minus 1, and you count down until you get to r minus n plus 1. Okay, so thinking about how we might use these Maclaurin series to our advantage, if you will, which function could we use to approximate square root of 1.5? So taking a look at these formulas, what would help us compute this hard number to a power of a half? And the key there is the power of a half. So if I take a look at this, this is like something to the 1/2 power. So if it's something to the 1/2 power, what if we did use the series expansion for 1 plus x to the 1/2 and evaluate the Taylor polynomials at x equals 0.5. Okay, so 1 plus 0.5 would give me square root of 1.5, and I could come up with the Taylor series expansion to do that for. So we saw in a previous video how we could compute the Taylor series. Now that we've gone to that work of generating, here's a formula for what we would use to set up that series, and then we would just evaluate, like, let's say our third degree Taylor polynomial at 0.5 to give us our approximate. So that's the kind of work that we did in our previous video called Taylor and Maclaurin series. I encourage you to take a look back at that. Let's do something a little bit new that we haven't done before, which is what if we derive our Maclaurin series from known series? So let's say we had to work with a function such as f of x equals cosine of the square root of x. That's a composition of functions, but we definitely know about the Maclaurin series for cosine of x. So because we do, we can use that information. So we know what cosine of square root of x is, and we know from our properties of power series that I can go ahead and compose these functions. So if I go ahead and take my cosine, it was negative 1 to the n, and then cosine is the even powers, and you put in here x to the 1/2. Simplifying that, we get negative 1 to the n, x to the n over 2n factorial, and we're adding from 0 to infinity are our terms. Okay, and then the issue of convergence, because remember, whenever we give a power series formula, we also need to talk about where it converges. So this is going to converge for all values where the inner function, square root of x, is defined. Okay, so cosine, the power series, converges on all reals, but square root of x isn't well defined on all reals. Remember, it's only defined for positive values of x. So on the interval 0 to infinity, this will converge. Okay, so see how fast and easy that was? It's really awesome. So now we have a tool, like if we wanted to approximate cosine of the square root of 1.5, we could do that. Okay, now let's take a look at another example. In part B, we'll be taking a look at doing this for the function sinh of x. And I brought this one up because some people have seen the hyperbolic functions, some people have not seen the hyperbolic functions, but the sinh of x is a fancy way of writing the following: e to the x minus e to the negative x over 2. And we can kind of use algebra to clean that expression up a little bit. E to the x minus e to the negative x, all of that times a half. Okay, so now I'm thinking about my properties of power series. What if we did 1/2 times the power series of e to the x minus the power series of e to the negative x So I have a half. This is cleaned up as much as possible. This is going to be -1 to the n, x to the n over n factorial. So from the ends, it's not really immediately possible to see like the formula for how this goes, but if we write out the terms, we might be able to see a pattern for it. So let's do that. We have 1/2 times 1 plus x squared over 2 plus x cubed over 3 factorial, so on and so forth, minus, okay, now this is where it's going to get interesting. This is an alternating, so it's going to start off positive 1 minus x plus x squared over 2 minus x cubed over 3 factorial plus x to the 4th over 4 factorial minus so on and so forth. So we're subtracting, because we're taking the difference, we're subtracting these two. So which terms are going to cancel? 1, so the evens cancel. The odds get multiplied by 2. So we have the half out here, and then we need to write the odds as two times x to the 2n plus 1 out of 2n plus 1 factorial and then we have a 2 that we can factor out that cancels with the half, and we're left with x to the 2n plus 1 over 2n plus 1 factorial. And where is it going to converge? Well, e to the x and e to the negative x, those power series will converge on all reals. So this is convergent on all reals as well, based on our properties of power series, which is that if you take these linear combinations of convergent power series, you end up with a convergent power series on the common interval of convergence. Again, you can refresh yourself on those properties if you take a look back at the properties of power series functions. Moving on to our next example, let's take a look at how we can solve differential equations with power series. So we can actually use a power series to solve initial value problems, and we'll do this on an easy initial value problem, but notice that we can do this on much harder initial value problems, and that's kind of what you're going to be using these for in the future. So let's say that we were trying to solve the initial value problem, y prime equals y and y of 0 equals 3. So I write my power series out for y. And we should leave that. We don't know what the constants are. So then the derivative y prime of x is going to be c1 plus 2c2x plus so on and so forth, n times cn, x to the n minus 1. Okay, so on and so forth. So if our y is equal to our y prime, then c0 plus c1x plus c2x squared, cnx to the n, then must equal c1x, c1 plus 2c sub 2 plus so on and so forth, n times c sub n, x to the n minus 1. So we're setting our two sides equal to each other. This is y, this is equal to y prime. So just substituting that in. And what does this imply? Well, it's going to imply that the coefficients on our x's have to be the same. So c0 doesn't have an x and c sub 1 doesn't have an x. So that implies that c sub 0 equals c sub 1. And moving on, c sub 1, x must equal 2 times c sub 2. And we can do this for every term. See, the pattern that's happening is we look to the next term and the previous coefficient will be tacked on. So 2c sub 2, in general, c sub n is equal to n plus 1 times c sub n plus 1. That's our general property that we have here. Okay, now we can use our initial condition. The fact that y of 0 is 3, I can go plug in and find that using our power series representation, c sub 0 must equal 3. So I can go back and say that, okay, so c sub 0 equals 3, c sub 1 equals 3. C sub 2 equals c1 over 2 will give me c2. So 3 over 2. C sub 3 equals 3 over c sub 2 over 3. So 3 over 2 over 3. So a half. And we see our pattern. Generalizing this, looks like we have C sub n is equal to looks like 3 is a common factor. So 3 times 1 over n factorial. So y of x then is equal to, come back, put your formula in, 3 times 1 over n factorial times x to the n, and you can pull that 3 out, and x to n over n factorial, well, that's just e to the x. So we just use this to solve our differential equation. Okay, and this takes a little bit to get used to. I encourage, if you're a little bit like, pause this, go back, watch that again, watch how we did that. We basically matched coefficients, and we looked at the pattern, and every time we would divide by the previous term over adding in n, the next term. So we were building an n factorial. Okay, so that's a cool application to solving a differential equation. Let's take a look at another application, which is using a Taylor series to evaluate a definite integral. This is a super common problem. Let's say we needed to express e to the negative x squared dx as a series. Well, we could express e to the negative x squared as a series and then integrate it. So negative x squared to the n over n factorial, using our properties of power series. This is negative 1 to the n, x to the 2n over n factorial, ranging from 0 to infinity. And we could go ahead and integrate that term by term. So it's equal to 1 minus x squared plus x to the 4th over 2 factorial minus x to the 6th over 3 factorial, so on and so forth. In general, we're getting the negative 1 to the n, x to the 2n over n factorial. And so when we integrate both sides, we get the constant of integration plus x minus x cubed over 3 plus x to the 5th over 5 times 2 factorial plus, minus x to the 7th over 7 times 3 factorial, leaving those factorials in there just to try to make the pattern very clear. And in general, what is the pattern? You have odd powers, alternating sums, odd powers, 2n plus 1, and then you have the odd that matches the power out in front of the n factorial. So in general, e to the negative x squared is equal to this expansion. Okay, we could use sigma notation if we wanted to. Let's see how we could use that to help us compute a definite integral. I have a formula for something I previously couldn't integrate. If I wanted to evaluate this integral that is otherwise impossible, by the way, to within an error of 0.01, I can use this power series to do so. So remember, we have a bound on our error from the Taylor series, right? The remainder theorem. That's one way of getting a bound on an error, using a Taylor polynomial, but this isn't quite a Taylor polynomial. We are also looking at what appears to be an alternating series. So instead of maybe using the remainder theorem that's kind of hard, maybe we could use the fact that we got an alternating series to our advantage. And we can. Okay, so specifically because this is an alternating series, we can use the remainder theorem from alternating series to find this bound. Okay, so what does the alternating series test say? You look to the positive, you take the absolute value part of your series, and then you look at the next term left off. So we want to go far enough out into our series where we're less than 0.01, like the next term is less than 0.01. So writing out what our series is, if we're computing the definite integral from 1 to 0, this is equal to this function evaluated from 1 to 0 for the x values. So the constant of integration is going to go away when we take the difference. So just cross it out, does not matter. Okay, and when I plug this in for 1, and then take the difference for plugging in 0, all the terms have x's. So the one plugging in 1, taking away when you plug in 0, the taking away 0 is just going to be taking away nothing. So all I need to do really becomes just evaluate at 1. Okay, so I get 1 minus 1/3 plus 1/10 minus 1 over 42 plus 1 over 216. And then let's actually check out what is our decimal for 1 over 216, because I think we're getting small enough to where we might be less than 100th. So the first term that looks like when I leave it off it'll be less than 100th is this one. 1 over 216 is 0.0046296. So 0.004, that means we're less than 0.01. So if we just take the first 4 terms, the remainder theorem says that the first 4 terms will give me accuracy so my max error will be less than 0.0046296 off. So I only need to add we're going to add the first 4 terms. And I've saved us the time of doing this on technology. Please don't be doing this by hand. It's so tedious. The whole point is kind of just understanding the cool power of math that we just did. So when we add up the first 4 terms, we get 0.74. And there it is. That's really awesome. So just kind of before we end here, think about the power of what we were just able to do. We took an integral that was previously not at all integrable. So if you tried to use any of the integration shortcuts that we have learned in this class, like all the tricks for integration, you would come up blank. And then you'd think, okay, well maybe there's some online calculator that can tell me what the antiderivative is. Answer, no, not with single variable calculus. So there is no algebraic technique for generating this antiderivative. You'll learn that there's a little bit more to the story in multivariable calculus, but computers and other devices, when they reach these integrals that there isn't like a known identity for it, it's using power series, it's integrating term by term, and it's then evaluating. by plugging in an x value. And it's very powerful to have something that's not integrable, and then now all of a sudden we can get an approximate for the value. And there's really cool applications to this particular integral e to the negative x squared in probability. Unfortunately, this is not an advanced stats class. That's a very cool class to take, by the way, but because it's not an advanced stats class, I will not force us to go into the depth of that. Application's a little complicated with a little bit of overhead and statistics, which isn't necessarily a class that you guys have taken quite yet. But just realize that probability curves are very related to this integral, so there's a lot of this kind of stuff that happens over there. Anyhow, no big deal. We just learned the main motivating factor for a large part of this class. Like, this is pretty powerful stuff. So this concludes our entire series of Calculus 2 videos. We end on this grand finale note, and in Calculus 3, you will learn all of the techniques of differentiation and integration and much, much more in 3 dimensions and more. So you've finished your study of single variable calculus, and now you're going to expand into 3 dimensions beyond and get so much more robust skills. So I sincerely wish all of you well in your further studies of math, and I do hope you continue on to multivariable. So see you later. Maybe never.